Okay, welcome to everybody. So this is an introduction to electronics. So what is it? So here you see an image in the background. There are a couple of oscilloscope, actually a spectrum analyzer, instruments, whatever things. So electronics is something that has to do with things like these things, circuits, electronic components. We have other things we will see different things during this course. You can find many videos on internet about such kind of things. What I think is interesting for us is to try to understand something about the theory also. So not only how to do things like connect this to this and this is black magic and it will work. You push the button and it goes, but also why it's working. So this will give you an idea of how to design things, not to just to copy like a recipe. So before going into this stuff, we have to do a couple of things. So we have to study a little bit of mathematics and a little bit of physics. Not that much, so I try to keep those things, let's say, at the minimum level we need for this course. But they are absolutely necessary because otherwise we don't have the tools in order to understand what we do in electronics. So let's start with the first topic. So we need to speak about vectors. So vectors is something that we already heard also during the high school. So if I draw an arrow like this, we have an intuitive understanding of what a vector can be. So we are used to think of vectors like a dot connected to an arrow pointing in a certain direction, having a certain length. So this thing is the length. And now I'm making an assumption by doing this vector on the screen. So I'm drawing a so-called two-dimensional vector. So 2D vector. So I'm drawing a vector on a plane. But vectors can be objects that, let's say, live in other dimensions. For instance, in 3 dimensions, this pencil here can be a vector pointing to a certain direction like this, or like that, or in other directions. So why vectors are important in electronics? Because at a certain point we need to study signals. And signals are, let's say, devices, objects, mathematical objects we will use in order to characterize physical variables. For instance, I always make this example. Let's say we want to consider the temperature in this room here as a function of time, for instance. So we can plot this number on a chart, and then we will see the temperature going up a little bit, then maybe down, then it stabilizes, then it goes down again and up again, and so on. So this thing is a physical variable, but we call it signal. In electronics, signals are most of the time, but not only, connected to electrical variables, something like currents, voltages, and maybe other things. So signals connected to concepts that goes around electricity. So what's the relation between vectors and those things? Most of the time we think that signals are functions like the temperature is is a function of time as the temperature is changing in time. So we will see that there is a connection, a sort of geometrical connection between functions and the concept of vectors. But in order to reach this connection, which is very useful in order to work with circuits and signals, we need to go a little bit deeper in the concept of vectors as objects that are not only in 2 dimensions or 3 dimensions, but let's say in n dimensions. So what does it mean? We will see in a while. So first of all, let's say that in order to speak about this topic, I will introduce a notation, mathematical notation, which originally has been developed by a scientist of the past whose name is Dirac, this guy in the picture here. So we will not make use of this notation as physicists do, but let's say we will abuse it a little bit in order to take advantage of what we need to do. So in this notation, he developed an idea which is very clever in order to have a sort of shorthand, so to be able to write long vectors, which for us means vectors in many dimensions, in a short way. So he introduced this symbol and this other symbol to indicate so-called row vectors, like this one, and column vectors, like this one. So for the moment, let's consider vectors as a collection of numbers. So the numbers are those ones. Like this, sorry. Those are numbers. These are n numbers, a1, a2, a3, and then an. And those numbers can be organized in a list. So for us, this is a list. You can imagine as a sort of box with sub boxes, and you put a number in it, in every place here. Lists of numbers. So the same thing we can do if we want to organize numbers in a list that we can write as a row. And those two notation, row or column, would be defined by those two symbols, this one and this one here. Okay, let's go on and let's see what we can do with this. So first we can define an operation among vectors. So if we have a vector we call A and B, we can summate and calculate A plus B, and this is a vector C. So let's give an example before we continue. So I switch from this view to another view, which is a sort of blackboard we have here. So I go here. Okay. So let's consider one elementary case. So I have what is called the Cartesian plane. So I put a label X and Y. So this is a reference frame from which we can start defining a 2D vector. So now I draw a vector like this, for instance, and then we probably know this. I can write this. I call let's say this vector is called A, and this is called AX, and this is called AY. So the two projection, as they are called, of a vector. So I can write this vector like this: A equals AX comma AY, or A equals AX and AY. Two different scripture, the same thing. So we are speaking about this kind of things. So if you have a third axis, it goes like this. So let's try to do in 3 dimensions: X, Y, and Z. Then we draw another vector. Something like this. Then we compute the projections. And this thing here is AX. This thing here is AY, and this thing here is AZ. And this one would be A equals, this is the vector AX, AY, AZ, or A equals AX, AY, AZ. So now we have to stop drawing, because you can imagine that by extending this concept, for instance, to 4 dimensions, I will have something like AX, AY, AZ, comma AW, for instance, but then it's difficult to do drawings in more than 3 dimensions. But ideally I can think of having objects like this as long collections, somehow of numbers, somehow associated to an abstract idea of a vector as a list of numbers. So now I go back to the presentation. Okay, so we were here. So here you have an example of what you can do with vectors. You can summate one vector with another one, and here you have the definition. So the definition of a summation of a vector is a vector having entries, and each individual entries is the summation of the individual entries of the vectors. So this. We can do for column vectors or for row vectors. Yes, column vectors and row vectors. It's the same. For now, it's just a way of arranging numbers in the list we have. Another important operation is called the inner product, which is indicated by this symbol. So by definition, the inner product is this thing. Now we will give an example of what it is. So how do we read this? I guess you know this symbol, sigma, capital sigma. So it stands for summation on the index k. So the definition of a inner product between a vector a and b is the summation of all its of the product of all its components a and b. So AK is the generic component of the vector A, BK is the generic component of the vector B. So if we take all of them and we summate like this, we have in the end a number. So this thing is a number, also called, let's say, scalar number. So a number like 1, 2, 3, it's not a collection of numbers, it's a single number, which is called the inner product. So let's make an example of an inner product, and before this, a summation between vectors. So I go back, I switch to the blackboard. So let's say we have a vector A equals, let's do the two-dimensional case, for instance, 1, 2. Let's draw this vector here. Let's try to draw this x and y. So how can we draw the vector A? Is the vector having x component equal to 1? So let's decide to have a 0 here, and this is a 1. And y component equals to 2. So like this. So the vector A is this one. Okay. Then let's consider another vector, B equals, I put small numbers, otherwise the chart gets too big, like 2, 3. No, sorry, let's change it. Let's put, for instance, 3, 2. To have a better visualization. So here we have 2, 3. So B is the vector having x component equal to 3 and y component equal to 2. And here it is, B and A in yellow. Okay. So if I want to compute the summation between those two vectors, let's call it C equals A plus B. So this is the vector AX plus BX, so 1 plus 3, comma, AY plus BY, so 2 plus 2, and this thing is, in this case, the vector 4, 4. So it's here 4, 1, 2, 3, 4. And here we have it. So if we do all carefully, then we will see that this thing here is parallel to this, and this thing here is parallel to that, and this is also called the parallelogram rule, geometrical rule to summate two vectors. Okay. Okay, so let's go ahead for other 10 minutes, maybe 5 minutes. before we stop this first part of the class. Okay. Oops. So now we want to give an example of this operation, the inner product. So again, we do this thing in the easiest case, so in 2 dimensions. So I go back here. Okay. Let's consider a vector A equals 1, 2, and B equals 3, 2. So when I say A, B, inner product between A and B, this thing is the row version of the A vector, 1, 2, multiplied the column version of the B vector, which I can write like this. And then I have to do this operation, so this thing is equal to the summation over the index k of AK, BK. We have only 2 dimensions here, so this thing is AX, BX plus AY, BY. And if we substitute for the numbers, then we have 1, which is AX, multiplied by 3, which is BX, 1 by 3. So this multiplied this plus 2 multiplied 2, which is this multiplied this. So this is what this means. And so this thing is 3 plus 4, which is a number, which is 7. Okay, so let's go back to the presentation. So what is this thing? So it is possible to demonstrate that number we calculated, so this thing here, corresponds also to this operation, where those 2 symbols here, this thing and this, is called the magnitude of the vector. In this case, the magnitude of vector B, which means the length. So this thing is length. And phi is the angle between the 2 vectors.